Hello. Came up in the previous video. I was mumbling to myself about how one might possibly take the integral from 0 to 2 of 2 to the x without the fundamental theorem of calculus. I think the actual problem was 2 to the x plus 6, but of course that can be split up into two pieces, and so maybe the more interesting thing is to ignore the 6 and to just ask, is this integral doable without the fundamental theorem of calculus? And I am going to explain how, yeah, you can do this. It's actually pretty interesting. Okay, how can we do this? First, let's get a picture going. So here we go. 2 to the 0 is 1, and of course, by the time you get to, well, at 1, it's 2, and at 2, it's 4. So we get nice exponential curve, and we would like to find the area under this curve. All right, so we're going to use the definition of an integral as the limit of a Riemann sum, and we will divide this integral up into subintervals. So delta x will be 2 over n, because we're going to use n subintervals, and the total width of the interval is 2. Let's use RRAM, because why not? And so you get like 1 over n, 2 over n, 3 over n, etc. Skipping ahead to I over n, which will be the right endpoint of the ith subinterval. And by the time I get there, I get some kind of thing like this. And then, of course, by the time you get to the nth subinterval, then this will be n times 1 times 2 over, oops, this is just all wrong. The delta x is 2 over n, so what I meant to say here was, it's a good thing I checked that, that's 2 over n, that's 2 times 2 over n, that's 3 times 2 over n, all the way until I get to I times 2 over n, and then the final rectangle, the nth rectangle, is n times 2 over n. I've multiplied by 2 over n times, and that's 2. Right, so that was actually a nice example of how checking your work shows that you're doing it all correctly. Alright, well, all that's fine. Now let's do it. Well, this integral, the integral from 0 to 2 of 2 to the x dx is equal to, by definition, the limit as n goes to infinity of the sum from I equals 1 to n of the function, which is 2 to the x, evaluated at the right endpoint of the ith subinterval. And so I'm adding up these n rectangles, and the ith one is going to have area 2 to the 2 over n times I times the width, which is 2 over n. Alright, all of that is completely fine, and really this is just the logic of representing an integral as a Riemann sum, and I haven't really used any particular fact about the function yet. And now the question is just like, can we do this, or do we just get trapped into some algebraic nightmare? And sort of shockingly, the answer is yeah, we can do this. And so we take the limit, as n goes to infinity, of, let's see, I'll pull out the 2 over n, leaving me with times, and now the thing that so far I think I did all this in the video. The thing in the video that suddenly gave me pause, and I might be able to actually compute this, is that this is 2 to the 2 over n I. In other words, using an exponent rule, that 2 to the 2 over n I times 2 over n could be sort of rewritten as, it's a very ugly sigma situation we got here, could be rewritten as 2 to the 2 over n to the I, showed me that this was in fact geometric. And so, okay, I don't know whether this helps or not. I think it does help. But so we can think of this as 2 over n times, and what am I adding up here? Well, when I is 1, I'm adding up 2 to the 2 over n. When I is 2, I'm adding up 2 to the 2 over n squared. When I is 3, I am adding up 2 to the 2 over n cubed. And now I keep doing this until I get to 2 to the 2 over n to the n. And that is indeed all that stuff in parentheses. Okay, kind of ran out of, let's do this. Cha, cha, cha. All that stuff in brackets is a geometric series, or the sum of the terms of a geometric, of the first n terms of a geometric series. And so, okay, we just know, because like, math, that a plus ar squared, all the way up to ar to the n is a times 1 minus r to the n over 1 minus r. This is just sort of a pre-calculus. And so, this becomes, over here, the limit, as n goes to infinity, of, well, there's this 2 over n that's just sitting out here doing nothing. And what's this? What's up with this geometric, what's up with the sum of the first n terms here of this geometric series? Well, the r in this case is, well, okay. A is the first term, which is 2 to the 2 over n. 1 minus r is itself, each time I multiply by 2 to the 2 over n. So that's 2 to the 2 over n, but all of that is then to the n over 1 minus r, which is 2 to the 2 over n. Okay, so I mean, we're not really doing anything sort of deep here. I'm just observing that that this sum is geometric, with r being 2 to the 2 over n, and also the first term is 2 times 2 to the n. Okay, is this doable? I think it is. What we get here is, let's see, we get the limit as n goes to infinity of 2 over n times, what does that whole top turn into? Well, 2 to the 2 over n to the n is, by exponent rules, just 2 to the 2. So that whole thing becomes negative 3. So we get negative 3 times 2 to the 2 over n over 1 minus 2 to the 2 over n. Okay, so getting the negatives out of there and stuff, I get the limit as n goes to infinity of, let's see, what did I do? I didn't do anything. Oh, yeah. Okay. So this is 2 over n times 3 times 2 to the 2 over n all over 2 to the 2 over n minus 1. And I think I just, on a hunch, just took that 2 over n and just stuck it up in the numerator. Okay, so, good. What is this limit? If I can somehow figure out this limit, so I made it through like stage 1 or whatever, which is I was able, because it's geometric, to come up with a formula for the Riemann sum. Now I just need to be able to evaluate this limit. Alright, and certain kinds of fancy people are now going to use some certain kind of fancy rule right now, but let's say I don't know that rule, I won't even mention it. As n goes to infinity, what's happening here? Well, it's not totally clear, because as n is going to infinity, 2 over n is going to 0, 2 to the 0 is 1, so this is like a 0 down here, And of course, as n goes to infinity, 2 over n is also going to 0. So this is like a 0 over 0 situation. This 2 over n thing is kind of annoying, so we're now going to do a variable substitution. So let a be 2 over n. And now just observe that as n goes to infinity, a goes to 0 plus. And so I may convert this limit into the limit as a goes to 0 plus of 3a times 2 to the a all over 2 to the a minus 1. Okay, what's up with that? Is this somehow doable? Well, I haven't really made any progress from the previous line. If I try to plug in 0 for a, I still get 0 over 0 situation. And now there's just this kind of wild moment where we somehow figure out how to do this. And here is the answer. It took me a while to figure out that this was even a good idea. Just put this down. So it's like this. I'm going to split this into the limit as a goes to 0 plus of 3 times 2 to the a, and the limit as a goes to 0 plus of a over 2 to the a minus 1. Okay, and of course, as a goes to 0, this one goes to 1. So this limit on the left is going to turn out to be 3. And what is this limit on the right? Well, it's going to be 3 times, and this looks suspiciously familiar to me. And so I'm going to write this as the limit as a goes to 0 plus of 1 over, well, then just reciprocating this, it's 2 to the a minus 1 over a. 2 to the a minus 1 over a. And I might even write this as a over 0. And now, observant people might recognize this as some kind of change in y over change in x type thing. And indeed, I guess I need to make some space. Indeed, this is derivative. And so, my sort of almost final answer here is that this is 3 times 1 over whatever the limit as a goes to 0 is of 2 to the a minus 1 over a minus 0. And when you write it like that, we see exactly what that limit is. It is, given the function 2 to the x, and given a sketch of that function, and given that this is the point 1, 0, and given that this is some point a, which is a tiny bit more than that, so this is up here at a comma 2 to the a, then 2 to the a minus, so then we can draw in this secant line, and we can see that the slope of this secant line is, on the one hand, a, and this is 2 to the a minus 1. And so indeed, we interpret this as a change in y over change in x, and as a goes to 0, this purple secant line becomes the tangent line. And it is simply a fact that this function, well, if you differentiate this, then you get ln2 times 2 to the x, and so the slope of the tangent line to this curve at 0, the slope of the red line, is just, well, when you plug in 0, you just get ln2. And so the ln2 sort of just is the slope of the tangent line to the curve y equals 2 to the x at x equals 0. And therefore, this is 3 over ln2 And that is the answer to this integral, which of course can also be done with the fundamental theorem of calculus. Woo!